Welcome to the Foundry by Forge College. I'm absolutely thrilled to have you here today. Go ahead and grab your digital hard hats, because in today's explainer, we are rolling up our sleeves and physically building a fully reproducible data processing machine for the Cloudbreak capstone project. If you've been following along with the course, we've done all the planning, we've gathered the theory, and now it's time to actually build something tangible. Let's get right into it. So here is our engineering blueprint for today. We're taking you step by step from raw data materials all the way to a functioning, reliable Python analysis script. We'll go from theory to code, equip your lab, build the script, bulletproof it with tests, draft the ultimate runbook, and finally wrap up the capstone. It is a packed agenda, so let's just dive right in.
All right, section 1. From theory to code, blueprint to machine.
Think back to what we accomplished in our previous lesson. You created this really incredible blueprint, right? Laying out your hypotheses, selecting your datasets, and mapping out your ETL, your extract, transform, load methods. Now we're transitioning into the machine phase. We are actually assembling the precision machinery that will take that exact blueprint and generate real empirical evidence. We're talking about a runnable script, totally deterministic output, and tangible CSVs and figures. It's where the magic happens.
Okay, moving right along to section 2, equipping your lab, setting up the workbench.
Now, you wouldn't try to build a high-precision engine on a completely messy desk, right? Well, the exact same goes for data science. Strict repository organization acts as the absolute foundation for your project. You've got your data folder for your CSV and Parquet snapshots. You've got your SRC folder specifically dedicated to your main Python analysis script. And finally, your outputs directory. That's basically the designated landing zone for all your summaries and figures. This layout ensures that your dataset paths are totally predictable and, more importantly, clean. Which brings us to section 3, building the script, writing the code. This right here brilliantly illustrates our data assembly line. It's just a beautiful, logical 4-step process. First, we load the data, so the raw account and transaction data goes in. Second, we clean that data, scrubbing it for any duplicates or nasty errors. Third, we transform it, aggregating it into meaningful, useful summaries. And finally, step 4, we output it. We safely ship out those process results. It's really like an elegant, totally repeatable factory line. The really crucial point here is that step 4 of our assembly line spits out this highly precise, comma-separated summary table. Take a look at these columns. You've got owner program, account count, mean size, and total LAM ports. This exact output, this specific CSV file, is now totally ready to be seamlessly consumed by our final capstone paper. There is absolutely no manual copying and pasting here. The machine does all the heavy lifting for you. Let's see how this builds into our final visual output. Because the script doesn't just make tables, it draws our charts too. Here we see a totally clear, fully reproducible bar chart of the top 3 owner programs by account count. So you've got the system program, token program, and associated token. And because our machine generated this directly from the data, it is completely empirical, verifiable, and perfectly accurate. No guesswork involved whatsoever. All right, section 4, bulletproof with tests. Embed assertions. Listen, a good lead engineer doesn't just build a machine and walk away, hoping for the best. They test it heavily so unexpected data gremlins don't get stuck in the gears. We tighten the bolts on our machine by adding embedded assertions directly into our Python script. We're explicitly checking that no account ID is null. We verify that our slot ranges perfectly match the analysis window we defined way back in lesson 1, and we confirm that our row counts are actually greater than 0. If the data doesn't match our strict expectations, our script fails fast, and it feels loud, which honestly is exactly what we want it to do. And that brings us to a massively important concept: deterministic output. What this really means is guaranteeing that if you run the exact same code on the exact same data, you get the exact same result every single time, no matter what computer you're running it on. Pinning your Python dependency versions and carefully managing floating point rounding errors, that's basically the duct tape of data science. It is absolutely essential to achieve perfectly deterministic, reliable outputs that you can actually trust.
Next up is section 5, the ultimate runbook instruction manual.
Every great piece of complex machinery needs a user manual, right? I mean, you wouldn't buy a car without one. For our analytical engine, your runbook isn't just some casual README file you throw together at the last minute. It is a precise set of instructions. It literally must include the required Python version, the exact terminal commands to create the virtual environment, example arguments to actually run the script, and a totally traceable mapping to your ETL plans.
Doing this allows any peer reviewer to reconstruct your environment without having to sit there and guess at your configuration. This whole concept of traceability, it is absolutely paramount. As you engage with the various advanced learning programs here, you're going to find that proving your work is exactly what separates a good student from a truly great engineer. Every single code block must have a one-to-one mapping to a documented method in your ETL blueprint. It proves beyond a shadow of a doubt to anyone reviewing your work that your code does exactly what your research framing claimed it would do.
Let's head into our final section, Section 6, wrapping up the capstone, final verification.
So before you finalize everything and call it a day, you absolutely need to run through this final checklist. Run your script end-to-end from a totally clean environment. Physically open your generated CSVs and confirm that they have the exact header names your paper requires. Look at your generated PNG figures. Are they actually readable at a standard size? And finally, ensure that every single one of those embedded assertion checks we talked about passes smoothly. This checklist is your guarantee that your machine produces perfect empirical evidence.
So, I'll leave you with this final, kind of provocative thought. Are your artifacts truly, fully reproducible, or are there still gremlins hiding somewhere in your machine? As you prepare for the formal technical write-up in the next lesson, really ask yourself if a total stranger could run your script perfectly using just your runbook. Thank you so much for joining me on this explainer. Be sure to visit forge.college to learn more about this subject, dive deeper into the capstone project, and explore other incredible Web3 engineering topics. Keep building, and I'll see you in the next one.